Okay, welcome student. With our second session now, as I have said, we were just touching the part of factor theorems with the part of polynomial functions. Now let us check the next part. This one is referred as to extended factor theorems. We call it extended factor theorems. How it states, extended factor theorem says, if d of x and any of x are factors of p of x, we say then h of x, which is a result of d of x times any of x, is also a factor of becomes also a factor of p of x. Becomes also a factor of p of x. So this is called the extended factor theorem. You can just take a count example of just a numerical number that suppose you take 12 divided by 3, we can say divided by 3. You are getting 4. Take again 12 divided by 2. You are getting 12 divided by 2. Let's say divided by 4. Let's say 12 divided by 4. You are getting what? You get what? 3. Now take this result. I could say 12. Yes, I could take 12 divided by 2. You are getting 6. Now take the result of 3 and this 2. 3 times 2, 6. So if you take 12 divided by 6, you get also. So we say, this is the way you can see. We say if A is a factor of D and P is a factor of D, then A times D must be the factor of P as well. So this is the idea that you have two factors of a function P of x. One factor is called D of x and another N of x. So if you multiply these two factors, which are all together factor of P of x, therefore the result is called H of x, and it must be also a factor of P of x. Let's check the example. Work the example here. Work the example. This one says, find the third factor of P of x equals to, find the third factor of x power 3 plus 2x squared, and then here we have minus x minus 2. Find the third factor of this. If x plus 2 and x minus 1 are its factors. A solution on this means we would be finding h of x, which is a result of x plus 2 and x minus 1. So we are taking the product of the first two factors. Expanding this carefully, x squared plus x minus 2, because we have this, and then so expanding, yes. So from there now, to find the third factors, we simply perform long division methods, taking our function, which is x cubed plus 2x squared minus x minus 2, and here so dividing by x squared plus x minus what? Minus 2. So we say which numbers must be setted here? We say which numbers must be setted here? This is supposed to be x here, x power 3, and here giving x squared and 2x. Yes. So subtracting this vanishes here, x squared here becoming positive x minus 2. So which numbers must be set? Is 1. So 1 multiplying is giving the same result this. So this vanishes. So upon subtracting. Therefore with this class, it means this one must be the third factor. So we say therefore x plus 1 is a third factor. So this is how we say, you can see how extended factor theorem works. And we will see this for the classwork at the end of our session. Now we switch for another part with this topic of algebra. This one is referred as Zero's theorem. Zero's theorem. Zero's theorem. Can you tell me, do you know the concept of Zero's theorem? And have you ever come across with this term? Without knowing, you have been dealing with this concept by intellect. You were solving in Form 2 quadratic equations, getting the result. And the name of those results, we were calling it as the roots of the quadratic equation. Now, always the roots. The best mathematical term to call it for roots is zeros. So we say, given a function p of x, p of x equals to expression in x. We say then, if p of a equals to 0, then x equals to a is referred to its 0. So it means to find zeros of a function, we simply perform factorization, which we are already aware with the concept. We simply perform factorization and again then set the function equals to 0. Then we say, to find zeros, we simply factorize. And then solve the function equals to 0. That is how we say. So there is nothing new. Finding zeros is nothing. It's just factorizing the function and then solving the function equals to 0. That is what we call zeros. Now let's look worked examples. Let's check worked examples on this part. Worked examples. Here it says, find zeros in A1. Find zeros in, I can start with the easiest one, which is the question we have been dealing with. Find zeros in f of x equals to x cubed plus 2x squared minus x minus 2. I have just copied this. 2. Find zeros in p of x equals to, let's find zeros on this case here. Let's check our zeros on this. With 3x power 4 minus 2x cubed. We want to check our zeros. Minus the 13x squared. And then we have plus 8x plus 4. 3. Q of x equals to x cubed minus 7x squared y plus 7xy squared plus 15y cubed. So these are some counter examples. One could ask us to find zeros with this. I can give another one here for any of x equals 2. Here we can have x cubed minus that is plus 2x square. Yes, we have this already. This question I'm having already here. So there is no point on this. Maybe let's change this to make it x cubed minus 1. Yes, let's make that. Solution on this with zeros. Starting with 1. We say we simply factorize. Now I'm not going to waste my time factorizing, because we know using factor theorems we have performed the concept of factorization. So factorize, for example, factorizing this, becoming p of x equals 2, we have already factorized it. We have our results, which was x minus 1, x plus 1 plus 2, x plus 1. Completely factorized, which was our result of factorization, x plus 2, x minus 1. So factorizing this, we simply factorize. So this factorized, we say then set p of x equals to 0. Upon setting this with the function equals to 0, this is now easy to say x minus 1, x plus 2, x plus 1 equals to 0. Solving for the result, now we have x equals to 1, x equals to negative 2, x equals to negative 1, hence zeros. So these are the zeros of the polynomial function, where we simply factorize and then solve equals to 0. Solve for the function equals to 0 and hence factorize it. You can see how it is interesting. So we will be checking again question number 3 and 2, and then you can see how it works. Let's go. Let's go. Okay, now we have seen how we could find zeros with question number 1. Now I'll be taking you with question number 2 to find our zeros. So with our question number 2, we say 2, upon factorizing, our function will be appearing as x minus 1, x plus 2, x minus 2, 3x plus 1. We have, if you factorize carefully, we must be getting this result because we know how to factorize. So to solve this, we say setting the function p of x equals to 0, and then it is now giving us x equals to 1, x equals to negative 2, x equals to positive 2, and x equals to negative 1 over 3. So these are the zeros. So I could be checking again question number 3, which we say also upon factorizing question number 2, we have seen how the factorization of this expression could go about. Factorizing this, it could be giving the function is q. So we say q of x, this becoming x minus y. Upon factorizing x plus y, sorry, and this must be x, factorizing the result, minus 3y, and next we will be having this result of x minus 5y upon factorizing. So we want to find the zeros. So again we say setting in the same way, setting q of x equals to 0. When we set this, giving x equals to negative y, x equals to positive 3y, and x equals to 5y. So this is how we could be finding zeros of the polynomial function. But we can ask ourselves, there are some situations in which you try to perform a factorization. Factorization does not work directly by using inspection method of checking the factors of the constant number. So in that cases, we go to the part we call this as rational zeros. So let's check this. Rational zeros. Rational zeros. Rational zeros. It must be coming from factorization. We say, suppose we need to find zeros in f of x equals to, want to find zeros in, suppose let's look this. Suppose you want to find 12x cubed, and here we have plus 16 x squared, and here we say minus 5x and finally we have minus 3. Yes. We say, suppose we need to find zeros in that function. We could be performing factorization first, using factorization using relational theorems. We say using factor theorems. So factor theorems, we said testing for the factors of this. So we say solution here, solution we say testing for factors of testing for factors of negative 3. So we say this is plus or minus 1 plus or minus 3. So from the function, when you try when x is 1, f of 1 does not give 0. So trying x equals to negative 1, p of this is our function f, and here also f of negative 1 does also not give 0. In the same way, you want to check 3 again. F of 3 does not give 0 as well. Testing f of negative 3 does not give 0. So in that juncture, for the situation like those ones, when we want to find the zeros in that case, when you find all numbers tested, which are the factors of the constant term, does not bring the function giving 0, so that you can start there on factorizing, and then at the end finding the zeros. In that case is when you note that there must be, we call it as rational zeros. Now how do we find rational zeros? Factorization by rational zeros, we say, to factorize here, we use ratio numbers. We use ratio numbers. It means we check all factors of this number, factors of negative 3, which is plus or minus 1, plus or minus 3. And again we check factors of 12. Here is 1, 2, 3, 4, 6, and 12. There must be plus or minus, of course. Plus or minus, plus or minus, plus or minus, plus or minus, plus or minus. So factors of this number must be the numerator and this one. So we test a lot. So you start testing. 1 over 1 does not add. 1 over 2. So 1 over 2, 1 over negative 2, 1 over 3, 1 over negative 3, 1 over 4, 1 over negative 4, 1 over 6, 1 over negative 6. It keeps on going. You come 3 over 2, 3 over negative 2. You keep on testing up to 3 over 12 and 3 over negative 12. So there are so many numbers in between here, numbers to test. So it is always a tiring task, but no way out. That is why few people has been coming to mathematics. So in that case, testing carefully here, checking very, very carefully testing. If you try x equals to 1 over 2, you'll find this function, our function f over half, this has given 0. So testing again, x equals 2, these numbers must be tested, all of them, discarding the repeated numbers. So testing again, when you test x is negative 1 over 3, f of negative 1 over 3, this one is also giving what? 0. Keep on testing again. Testing x equals to negative 3 over 2, this one also f of negative 3 over 2, this one is giving 0. Therefore, in that case, so we say this is a trick for rational zeros, where our zeros now becoming zeros. Zeros are zeros in this case, becoming x equals to 1 over 2, x equals to negative 1 over 3, and x equals to negative 3 over 2. So these are the zeros from rational zeros. A very, very challenging part, but needs for a student to be intelligent enough. Okay, thank you. Now we will be checking the next part. This is called solving simple polynomial functions. You will be given some simple polynomial function where you will be required to solve. Let's go. Okay, now we have seen, student, how it is interesting with the part of algebra, and you can see how it is too much applicable in the real life situation. So now I'm taking you to the next part. This one is involving the concept of location theorem on algebra. When we know the idea of zeros theorem, zeros, mind you, that is simply a root of a polynomial function. So you can be asked to test which position that root is appearing, or that zero, which position. So we say, we take this part, we call it location theorems. Location theorems is nothing. We say, consider the figure below. When we have a figure like suppose you can have a figure like this, and then we have something like this. This is our x-axis, and here we have y-axis here. So imagine you have a certain function. Let's say this function. There is a number here before the function cuts, call A, and there is a number here after the function cuts, call B. This function is called y equals to f of x. When you find f of a is a number less than 0, because the result a cuts the function here down. So here, that is why there is f of a. And b, the value of b here, that is why there is f of b. It means also f of b is greater than 0. So at the position where f of b is giving positive, f of a is giving negative, it means the graph is closing somewhere. So we say, so when you take f of a times f of b, the result must be 0, which is a condition, which is the condition that there exists a root between A and B. So that is a condition for location theorem. That when one is asking you, verify that there is a root between A and B, you must find the replacement of A and B. The product of the two replacements, if gives negative number, it concludes that there is a root between that number. So let's look at this. Let's check the worked example. One can say, verify that there exists a root of p of x equals to, verify that there exists a root of p of x equals to x squared minus x minus 6 between we can have between 2 and 4. Look this question. Verify that there exists a root of p of x between 2 and 4. So there we simply proceed like this. We simply check if p of 2 times p of 3 is less than 0. P of 4, I mean, sorry, p of 4. We simply check if p of 4 times p of 2 times p of 4 is less than 0. So let's find p of 2. P of 2 from the function 4 minus 2 minus 6. This gives negative 4. P of 4, that gives 16 minus 4 minus 6. That gives positive 6. So P of 2 times P of 4, that is giving what? negative 24. This time this number is 0. So hence verified that there is a root between 2 and 4 for this function. Finding that root is when we will be going for zeros theorem, factorizing and finding the zeros. So we say hence verified. Hence verified. Hence verified that there is a root between in that one. So that is a concept. So you will try this. Try this. One can say locate appropriately the roots of locate appropriately the roots of f of x equals 2. We can have x cubed 7x squared, and we have plus 3x here, and then here it says plus 17 in the interval of x greater or equal to negative 3 less than 8. So you can try this one using the same trick, but table values also is very useful to make appropriate. It means you will be hinting, you will be making a table value, putting x from negative 3 to 7. When x is negative 3, put. When x is negative 2, put. And so where the number changes, positive values of y, positive and negative, the root ranges in that position. So with that one, let's look this part. We call solving simple polynomial function. Solving simple polynomial function is nothing difficult. We simply have to work carefully. We say we simply use suitable trick. So we say worked example. Let's check some worked examples here. Worked examples solving simple polynomial functions says solve. One is 1. You are given a question like x squared plus 4 over 3 plus 4 over x squared plus 4 and equals to plus 4x here equals to 11. Question number 2, one can give us a question like 5. You will see this in Advanced Mathematics by Tranta. This one, okay, minus x minus 1, and then here equals to 2. One can give also another question like 2x power 4 minus 9x power 3 and plus 14x squared minus 9x plus 2 equals to 0. These are just some. It is simple to solve this one. For example, looking for question number 1. Using for question number 1. To solve this one, you can just let this part, call it as a over 3, and they are becoming 4 over a again equals to 11. So you can multiply by 3a both sides, becoming a square plus, because 3a, a3 will be cancelling. So 3a also here, a is going to cancel, will be giving 4 here. And here this side will 33a. So it means you have quadratic a minus 33a plus 4 equals to 0. In this case, simply perform factorization, checking the number which holds for solving. It means here we have multiplied. Here times 3. Okay, times 3. Sorry. Times 3, this was supposed to be 12. This number is 12. Yes. Supposed to be 12 here. Because when say 3a times, a is going to cancel. But here 3a here, a is going to cancel. but 3 and 4, 12. Okay, with this one, 3a, 33. So 33a. So it means solving this, you just go to calculator, trying to perform this result to check. So using a, going to calculator, trying to solve this. Mind you, this is supposed to be 12 here. So you simply get the values of a. Once you know the value of a, coming to plug here to know a is x squared plus 4x, using simple calculator, you'll be getting 4 possible results. In the same way with 2, with this one, you use this trick here, 5x minus 25 radical. You can be intelligent enough, bring one term to the other side, becoming 2 plus x minus 1 radical. So the trick here is, what is the trick here? Performing squaring both sides, and performing squaring both sides. This one, making the radical vanishes, so 5x minus 25. But in this case, giving 4 plus 4x minus 1, but plus x minus 1. You will be correcting like terms together. Bringing this x to the other side, we will be having 4x here. But this 4 and the negative 1, that is 3. Bring to the other side 28. While this side is 4x minus 1 radical. Dividing by this for both sides, you are getting something like here, which is x minus 7. While this side becoming x minus 1 radical. Squaring both sides, giving squaring both sides with this term here. When you perform squaring both sides here, it is really simple to say x squared minus 14x plus 49, while this side becoming x minus 1. So you are making correcting like terms together, minus 15x plus 50 equals to 0. I'm not teaching how to solve quadratic. Here we can say easy to finish. Easy to finish. In that juncture, it could be so interesting also with this number 3, where you can use zero theorem or you can use a trick. So I'm giving only a hint with 3. With 3 here, we call it symmetrical function. Why do we call it symmetrical? You see the numbers 2, 2, 9, 9. So we always want to divide by this variable which is different from the others, x squared. It takes the coefficient which is unique. So divide by x squared both sides. We say dividing by x squared both sides. This one could be becoming 2x squared. This one could be becoming 9x. This one could be becoming 14. While this could be 9 over x. And the next 2 over x squared equals to 0. Then you could be collecting, bring this 2 here, x squared plus 1 over x squared. And again, bring with terms with, bring 9 here, x plus 1 over x. And this 14 equals to 0. When you are in this case, we say let x plus 1 over x equals to p. Expanding x squared plus 1 over x squared will be becoming p squared minus 2. So wherever x squared plus 1 over x squared, put p squared minus 2. And wherever there is x plus 1 over x, put p. Condensing the equation will be giving us a quadratic, which hands out and becomes simple to conclude. Okay. So I'm going to give you a classwork, an exercise for questions, in which you'll have to check so that when we meet next time, I can be checking your progress. Okay, let us have a classwork here in which you'll have to practice. So we say classwork here. Classwork we say 1, use remainder theorem. Use remainder theorem. Use remainder theorem to find remainder error when the remainder error when a f of x equals to, we have this function here, we have this function when f of x equals to x power 3 plus minus 6x squared plus 11x minus 6 is divided by x plus 7 using remainder theorem. B, we can have another question here. This is an interesting one. Let's check on this. This is a nice one. We have here, it says when the function g of x equals to 8x power 9 plus 7x power 7 minus 13x is divided by 3x plus 5. So question number 2 one says factorize completely. Factorize completely. Given this, it says factorize completely. Factorize completely, we can have this a, which we have p of x equals to x power 3 minus a power 3. And the b, we can have f of x equals to x cubed plus 3x squared. And then plus 3x. And here plus 2. So you can be practicing for factorization. And then let us look at another question. This one is for solving. We can say find zeros in h of x equals to x power 3 plus a power 3. B, we can have this one here. This is p of x equals to x cubed minus 6x squared plus 11x minus 6. So here we want to find zeros on that one. So with that one, I think we will be having some part to enjoy. Do not forget to consult us with your message. From WhatsApp, you can make a messaging, or you can give us a message in WhatsApp or just an SMS, or you can follow us in the Instagram page called the Elimika Darasa, or in YouTube you can subscribe in the heading Elimika. So all these communications will be channeled through 0769 048 594. Thank you very much. Thank you for listening. Thank you for watching.